What if I tell you that there is a battery that will last you more than 50 years? Will you believe it? Well, if you believe it or not, but seems like this is the reality where we are going to. A groundbreaking development has been announced by a Chinese company signaling plans to enter mass production of miniature nuclear batteries with an astonishing lifespan of up to 50 years. This revelation places them in potential competition with British and American companies that have been striving to introduce similar products to the market for several years. Just imagine a battery that can last 50 years will change the way we see the future right now. The phones, all kind of medical devices, and everything else that runs on a battery will be tremendously more powerful and more efficient. Let's see how far we have reached and how behind we are from this Chinese company that is claiming that they have already manufactured batteries that can last for more than 50 years and that will be available for public or consumer use. Contrary to the common perception of radioactive materials as inherently hazardous, their ability to emit energy presents an intriguing opportunity for efficient and long-lasting batteries. The principle behind these nuclear batteries lies in leveraging materials with extended half-lives, potentially allowing them to operate for thousands of years without the need for recharging. The concept of nuclear batteries is not entirely new, particularly in the realm of medical devices, where the hazards associated with the battery replacement are a significant concern. In the 1970s, pacemakers were equipped with plutonium-powered batteries, and remarkably, some of these devices are still functional today. In recent times, lithium batteries have gained prominence in medical devices, necessitating replacements every decade or so. But this is 2024, and now we understand that nuclear energy is not as deadly as we used to think. So, the announcement by the Chinese company BetaVolt can be a great start of the revolutionary battery technologies that we can use in our everyday lives. If successfully implemented, these nuclear batteries could revolutionize the longevity and sustainability of our gadgets, mitigating the need for frequent recharging. This battery is introduced by BetaVolt operates on the principle of voltaic technology, specifically utilizing beta decay. This technology falls under the category of beta voltaic batteries, which harness the emission of electrons during beta decay to generate electricity. To accomplish this, BetaVolt employs nickel-63, a radioactive isotope with a half-life of approximately 100 years. This isotope is strategically placed between diamond semiconductors, incorporating a p-n junction. The energy conversion rate of the battery reaches 8.8% from the energy incident in the diamond semiconductor transducer, and the power density of the battery will be further increased if a higher purity nickel-63 radioactive source is used. But this is not the only company that is working in this technology. Several companies are currently involved in the production of nuclear batteries powered by tritium decay, primarily utilized for scientific or medical purposes rather than consumer applications. But there are limitations, which lies in their relatively low power output, typically in the range of nanowatts or microwatts. For perspective, consumer devices like phones require a few watts, rendering these nuclear batteries unsuitable for direct replacement for conventional power sources. However, their appeal lies in delivering low power consistently over an extended period. The rest of the world is not far behind this Chinese company. In Western world, some startups have garnered attention for their efforts to bring more potent nuclear batteries to the market. Notably, the British company Light, formed by University of Bristol researchers, aim to introduce small nuclear batteries using carbon-14 by 2024, providing up to 200 microwatts. Despite being on the higher end of the power spectrum for nuclear batteries, this remains insufficient for the energy needs of most devices. Though Light is working mostly on three types of batteries: diamond gamma voltaics, tritium beta batteries, and carbon-14 beta batteries, though all of them are in development. Another company, this time from the United States, Nano Diamond Batteries, attracted significant publicity with their claim of producing batteries that could last over 20,000 years using nuclear waste. However, recent months have seen fraud allegations against the company, accusing them of misleading investors by promoting technology that had not even been genuinely tested. Because of that, I have doubts about the company's credibility and operational longevity. Now, the question is, does it work? How much power will you need, and can this type of batteries provide it? The technology behind batteries powered by nuclear decay falls into two main categories. One approach involves utilizing a radioactive substance to generate heat and then leveraging the temperature difference between the two locations to produce a current. This method is known as radioisotope thermoelectric generator (RTG), a technology pioneered by the air forces of the United States and the former Soviet Union in the 1950s and 60s, initially and obviously developed for space missions, particularly in environments lacking solar powers. These RTGs have found diverse applications beyond their initial purpose. Now, the focus is shifting because while we are living in this world, we also need power. RTGs are pretty practical if you ask me. It has extended to various other fields because of their versatility and reliability. The European Space Agency, which was initially resistant to use the nuclear batteries, has recently shifted its stance. The turning point can be attributed, in part, to the challenges faced by the Philae probe during the Rosetta mission in 2014. The probe's batteries, intended to recharge through solar power, succumbed after 3 days due to its landing in a shadowed area on a comet, leading to the untimely conclusion of the mission. But again, the ESA is planning to employ a nuclear-powered spacecraft for its Argonaut moon lander, slated for launch in the early 2030s. However, the drawback of traditional RTGs lies in their considerable size and the inefficiency associated with the detour through a temperature gradient when the primary goal is electricity generation. To address these limitations, a more promising solution would be if we use semiconductors driven by nuclear decay for electricity generation. This alternative refers to as voltaic batteries, alpha voltaic, beta voltaic, and gamma voltaic batteries. Utilizes the direct conversion of nuclear decay into electricity. As you can understand, this approach presents a more efficient means of generating electricity, making it a compelling choice for applications where space and efficiency are critical factors. While the technical details may sound intricate, it's worth noticing that the semiconductor materials used in this nuclear battery is akin to the material commonly found in solar cells. In solar cells, the sunlight that induces a current, whereas in nuclear batteries, it's electrons emitting during beta decay that drives the current. But seems like BetaVolt's leading the race. Although the technology itself isn't entirely new, the company is making significant strides in transitioning these nuclear batteries into the consumer market. Their flagship product, the BV100 battery, boasts a power output of 100 microwatts and a voltage of 3 volts. Remarkably, it is comparable to the size of a typical cell battery, although you will need thousands of this to run a mobile phone. Let's see how far this race goes. After all, we'll have a technology that can last for more than 20,000 years.